In this problem, we're given a diagram that says that there are three charges as shown below that are located at the vertices of an isosceles triangle. We need to calculate the electric potential at the midpoint of the base, so right here, if each one of the charges at the corners has a magnitude of 5 nanocoulombs. Now we're given that the bottom two charges are negative 5 nanocoulombs and the top charge is positive 5 nanocoulombs. The equation that we want to use for the electric potential based on a charge is KQ over R. And so we're going to find the electric potential from each charge and then add them up. First, let's find the electric potential from the first charge, which again is KQ1 over R. K is Coulomb's constant, so it is 8.99 times 10 to the 9th, same as it has always been. But it is in units of newtons times meter squared per coulomb squared. So we need to make sure that our units are not nanocoulombs, but regular coulombs. We want to include negatives in this equation, so it's negative 5, and nano means times 10 to the negative 9th coulombs. We need the distance between where we are located, our x, and our first charge. So this distance is half of 2, which means that it is 1 centimeter. But we need our units to be in meters, so that's 0.01 meters. We get then that the electric potential is negative 4,495, and the units are volts if we kept things in coulombs and meters. Next, we want to find the electric potential from the second charge. So again, it is KQ2 over R. K is again 8.99 times 10 to the 9th. We want to change from nanocoulombs to times 10 to the negative 9th coulombs. And the distance is again 0.01 meters. The distance from the x to where our charge is located is 1 centimeter or 0.01 meters. This again turns out to be negative 4,495 volts. And then we want to find the electric potential from the third charge, KQ3 over R. K is again 8.99 times 10 to the 9th, newtons times meter squared per coulomb squared. Charge is a positive 5 times 10 to the negative 9th coulombs. And the distance, well, we don't know the distance, so we're going to have to calculate it. We see that our triangle here, highlighted, our triangle, has a hypotenuse of 4, and one of the sides is 1 centimeter. We need to find this side here. So we have Pythagorean theorem, the hypotenuse squared is equal to this side 1 centimeter squared, plus our unknown side, I'll call that side B squared. So the unknown side comes out to be 3.87. Units we've been using are centimeters. We're going to have to convert that to meters for our formula. So 0.0387 meters. We get a value then of positive 1,161 volts. And now what we have to do is we have to find the total. So we're going to add up those three numbers. So the total is negative 4,495 volts plus negative 4,495 volts plus 1,161 volts. And we get that the total, the electric potential, comes out to be negative 7,829 volts. So again, find the electric potential from each charge. Make sure you include any negatives for charges. Distances are always positive though. So include any negatives for charges, but distances are always positive. And then add them all up at the very end to find the total.